Hey everyone, and welcome to this explainer. I am absolutely thrilled to be your guide today. We aren't just going to rattle off a list of random disconnected chemistry facts. Instead, we're going to look at acids, bases, and salts as a dynamic, interconnected master blueprint of our physical world. By the time we wrap up, you're going to see exactly how these invisible chemical life cycles actually engineer the reality all around you. Okay, let's dive right into this. We've got 5 main stops on our journey today. First, explaining our raw materials. 2, visualizing reaction blueprints. 3, the neutralization principle. 4, synthesizing everyday salts. And finally, number 5, we'll look at some wild chemical anomalies and dangers. All right, part 1, explaining the raw materials, states, and strengths. So, if you want to build a universe, you need foundational building blocks, right? In our chemical blueprint, acids are some of those absolutely crucial raw materials. But to really understand them, we have to look at their core strength, like what actually separates a highly corrosive, strong acid, think hydrochloric or sulfuric acid, from a milder, weak acid like acetic or oxalic acid. Well, it all comes down to ionization. A strong acid completely ionizes. That means it fully breaks apart in water to release this overwhelming surge of hydrogen ions. A weak acid, on the flip side, only partially ionizes, so it releases way fewer hydrogen ions, making it much less volatile. Now, what's really interesting about this slide is the physical spectrum of these materials. We almost always picture acids as these aggressively bubbling liquids in a glass beaker, don't we? But nature is way more versatile than that. Yes, we have our liquid acids like nitric acid, but they can actually be solids too, like the tartaric acid you find naturally in fruits. They can even be gases, like dry hydrogen chloride gas. Because these raw materials can be pretty hazardous, we need reliable diagnostics to detect them. We use visual indicators like moist litmus paper, where acids will turn blue litmus red and bases turn red litmus blue. We even have olfactory sensors, which is just a fancy way of saying we use smell. If you mix an acid with onion juice, the onion smell stays, but a base will literally destroy the odor completely. And then there's the methyl orange test. In an acidic solution, the liquid turns a bright, vivid red, but in a basic solution, it shifts to this distinct yellow color. We can actually plot the exact intensity of these solutions on the universal pH scale. That scale runs from 0 to 14, with 7 sitting perfectly in the neutral middle. But the number 5.6, that is a critical metric you need to keep in mind. Why? Because the moment the pH of rainwater drops below 5.6, it crosses the threshold into the dangerous territory of acid rain. And as we know, that can totally devastate ecosystems and corrode our infrastructure. Naturally, dealing with these raw materials requires strict safety protocols, especially when it comes to the physics of dilution. The golden rule here is absolute. You must always add acid into water, slowly while constantly stirring. If you do the reverse, if you drop water into a concentrated acid, you trigger a highly exothermic reaction. That basically means it generates so much heat so fast that it causes localized flash boiling. The acid can splash out violently, and they're risking some very severe chemical burns. Moving on to part 2, visualizing reaction blueprints, the engine at work. And this brilliantly illustrates the core logic of how these chemicals interact. Think of an acid as the center of an engine. From that center, it can take 4 primary reaction paths. It can react with metals, it can react with bases, metal oxides, and carbonates. And the cool thing is, each specific pathway yields completely different, highly predictable byproducts. Let's zoom in on that middle pathway for a second, using sulfuric acid and zinc. When you mix them, they produce a salt, zinc sulfate, and hydrogen gas. But kinetics play a massive role here. If you use zinc dust instead of larger zinc granules, that massively increased surface area speeds up the reaction significantly, generating way more heat and hydrogen gas. And how do we actually prove it's hydrogen? We use this fantastic diagnostic trap. If you bring a burning candle near those escaping gas bubbles, it burns with this very characteristic, highly satisfying pop sound. Okay, so what happens on the carbonate pathway? Let's break down the sequence step by step. Step 1 is the input. We add an acid to sodium carbonate, which triggers a brisk effervescence, basically a whole lot of aggressive bubbling. Step 2 is the diagnostic. We take that escaping gas and pass it through lime water. The lime water instantly turns a milky white, which proves the gas is carbon dioxide, because an insoluble calcium carbonate precipitate has formed. But here is the fascinating twist in step 3, which we call the excess override. If you continuously pump that excess CO2 through the milky solution, it chemically converts that solid precipitate into soluble calcium bicarbonate, and the milkiness just completely disappears. That brings us to part 3, the neutralization principle, finding balance. You see, the chemical universe isn't just about explosive reactions. A huge part of it is about finding equilibrium. It's this delicate balancing act between two opposing, highly corrosive forces. And the core principle here is just beautifully elegant. When you take a strong acid and combine it with a strong base, they literally annihilate each other's corrosive properties to form perfectly stable salt and water. But here is a key insight to remember from this explainer. Metal oxides, like copper oxide or magnesium oxide, are fundamentally basic in nature. So reacting an acid with a metal oxide is, at its core, the exact same neutralization process as reacting it with a direct base. It's the same blueprint. And these abstract chemical equations, they're actually the invisible machinery running our everyday lives. Think about how we engineer this neutralization all the time. In agriculture, when fertilizers make the soil way too acidic to grow crops, farmers neutralize it by spreading basic compounds like quicklime. In medicine, when excess stomach acid causes you excruciating pain, what do? We ingest mild bases, antacids like milk of magnesia, to safely neutralize the threat right inside our bodies. Even in fire safety, the classic soda acid fire extinguisher relies on an acid and a base mixing violently when you strike it, releasing massive volumes of high-pressure CO2 to smother the flames. All right, part 4, synthesizing everyday salts, building our world. So what happens after all that chaotic neutralization? Well, you get stability. The final, stable products of our chemical life cycle are incredibly powerful. And by the way, salts are so much more than just a seasoning we sprinkle on our French fries. Remember that number 7 on the pH scale? It represents perfect neutrality. When a strong base like sodium hydroxide fully neutralizes a strong acid like hydrochloric acid, you are left with sodium chloride. It's a salt with a perfectly neutral pH of 7. It is the ultimate balance byproduct, mined from ancient dried-up seas, and it serves as the foundational raw material for so much of modern industrial chemistry. Let's move along and see how this actually builds our industrial world. If you take that basic salt water, which we call brine, and run a direct electrical current right through it, you initiate the incredible chlor-alkali process. This splits the brine apart, generating 3 highly valuable industrial outputs: chlorine gas at the positive anode, hydrogen gas at the negative cathode, and a liquid alkaline sodium hydroxide solution. Then, we take those outputs and synthesize materials that require incredibly strict storage protocols. Take bleaching powder, for example, which uses that generated chlorine gas. It's absolutely vital for disinfecting municipal drinking water, but it has to be kept in airtight containers. Why? Because prolonged exposure to ambient carbon dioxide in the air will slowly degrade its effectiveness. Now, contrast that with plaster of Paris, a synthesized material that must be kept entirely safe from moisture. If it gets even a little bit wet, it spontaneously undergoes a chemical transformation, locking in water molecules and reverting right back into a rock-hard, totally useless block of solid gypsum. Synthesizing salts also solves some pretty funny everyday culinary engineering problems. Take baking soda. When you heat it up in a cake batter, it creates CO2 bubbles that make the cake rise. Sounds wonderful, right? Well, the problem is, it leaves behind sodium carbonate, which is inherently basic and tastes terribly, terribly bitter. So what's the genius solution? We synthesize baking powder by mixing the baking soda with a mild edible acid like tartaric acid. When the batter gets wet in the oven, a mini neutralization reaction occurs right inside your cake. It completely destroys the bitter taste while keeping that perfectly fluffy texture.
Finally, part 5, chemical anomalies and dangers, the rule breakers.
You know, in chemistry, there are always those fascinating rule breakers that completely defy the standard blueprint we just mapped out. For our thrilling finale, let me pose a direct question to you. Almost all standard acids are safely stored in normal laboratory glass bottles, right? So why is it an absolute disaster to store hydrofluoric acid in one? What makes it so incredibly different? Well, the answer is that hydrofluoric acid chemically reacts with and literally eats the silica present in glass. It dissolves its own container, so it has to be kept in very specific plastics. And that's definitely not the only anomaly out there. Take the dry acid illusion. Dry HCl gas won't change the color of dry blue litmus paper at all because acidic behavior strictly requires hydrogen ions, and those only dissociate when water is present. No water, no acid reaction. Furthermore, there's the copper curd hazard. You can never ever store sour foods like curd or yogurt in copper or brass vessels. The natural acids in the food react corrosively with those specific metals, producing highly toxic chemical compounds that will cause severe food poisoning.
So the crucial point here is that you always have to be aware of the exceptions to the rules. Remember earlier when we said acids react with metals to produce hydrogen gas? Well, nitric acid completely defies this. It is such a powerful oxidizing agent that when it reacts with most metals, it immediately oxidizes the hydrogen that gets produced, turning it into water instead. It totally subverts the standard blueprint. And naturally, there's an exception to this exception. Magnesium and magnesium are the only two metals that will stubbornly still yield hydrogen gas when mixed with very dilute nitric acid.
So look at what we've covered. We've tracked the raw materials, we've mapped the reaction engines, found balance through neutralization, and synthesized the salts that build our everyday lives. But as we wrap up this explainer, I want to leave you with one final provocative thought. If our entire modern world relies on this incredibly delicate, perfectly engineered balance between highly corrosive acids and powerful bases, what happens to our ecosystem, our infrastructure, and our very bodies when we disturb that chemical equilibrium? Think about that the next time you use baking powder or walk past a fire extinguisher. Thank you so much for joining me today. Keep asking great questions, and I will see you next time.